So yeah, hi. My name is Honggyu Kim, and from SK hynix, and I'm going. My topic is the expanding the CXL software ecosystem through HMSDK on Linux, and so maybe the slide is There's some problem actually. Yeah, never mind. Okay, so in the conventional memory system consists of only the same types of memory in their DIMM slots. So it just works. So we don't have to have some kind of special software support. But expanding the memory beyond the DIMM slots, and so we can have CXL memory. And so having the CXL memory, we can expand the bandwidth and capacity, but it requires some of the software support for efficient use. So the software support for the CXL memory, and initially, CXL driver level support is needed, and then so the device driver is located in here in Linux kernel, and the memory management support is very much needed for the efficient use. And the CXL memory is detected as a CPU list NUMA node, and so we are working on based on the NUMA abstraction. So we are working on it under the HMSDK project. So HMSDK project. The HMSDK stands for the Heterogeneous Memory Software Development Kit, and it provides three different modes. And then the first one is a bandwidth expansion, and second is capacity expansion, and the last is a custom allocator. I'll go one by one. So the bandwidth expansion can be used when the target workload is bandwidth hungry. And in that case, and then so the providing more bandwidth, and so we can achieve the speed up for the bandwidth intensive workloads. But for the capacity expansion mode, and then so if the workload is not bandwidth hungry, but it requires more capacity, and we can expand the capacity with the CXL memory. But accessing the CXL memory requires additional latency, so we have to minimize those kind of latency over it. Yeah. And then the last one is a custom allocator, and this can be used when the user have some knowledge about their programs, and so we can modify the target program with HMSDK's hmalloc APIs, such as hmalloc and hfree. So that means and the custom allocator requires some software modification, but the first two modes doesn't require software modification because those are the OS level techniques. So maybe I can just skip this slide because I'll explain it in the following slides. So the first one is bandwidth expansion. So having the conventional, the round robin interleave can work, but it doesn't consider about the bandwidth characteristic difference. So it just distributes the pages evenly distributed, and so it doesn't consider the bandwidth difference. So having the weighted interleave, we can consider the bandwidth difference. And so having this one on the left side, so the host memory bandwidth is underutilized here, but having the weighted interleave, and so we can allocate two pages to the host memory, then allocate one single page to a CXL memory, considering the bandwidth difference, and so we can fully utilize those kind of bandwidth capability. Yeah. So this weighted interleave is provides some kind of sysfs interface in the kernel. And this is available from the Linux version 6.9. This is fully upstreamed, and then with the collaboration with the Memverge engineer, Gregory Price. And so in this location, and we can set the weight numbers, and then so the user interface, and so NUMA control is a widely used tool to set the memory policies, and so there's a new option called -w and -- weighted interleave, and then so we can specify some nodes, and so I'll show you the USG. And back to the similar picture, and then so we can just write the weight number to the node 1, node 0, and we can set the 1 to the node 1, which is a CXL node. And then in that case, and then the kernel is ready, but it doesn't work without the NUMA control. Because the NUMA control provides a dash weighted interleave, and then 0 and comma 1. And that means that run the target program with the weighted interleave for the NUMA node 0 and 1. And we can run the target program in a weighted interleave mode. So the performance result is shown in the below picture. And so having the 8 channel of DDR5 and plus and the 4 channel of CMM DDR5, and we are able to achieve a 21% of the throughput improvement in a 2-to-1 read-write ratio, and then in terms of the 1-to-1 read-write ratio, we are able to achieve 31% of the performance, the bandwidth expansion. Yeah. So the second one is capacity expansion. And before explaining about the capacity expansion, and so I need to explain about this new feature, and then which is called the DAMON in the Linux kernel. And DAMON is a data access monitoring framework in the Linux kernel, and that is supported from the version 5.15, and that was released about 3 years ago. And it allows memory access checks in an upper bounded overhead for scalability. That means that it sacrifices some of the accuracy. In the below picture, and it shows a heat map, and then from left to right is time, and then from the bottom to up, and these are the address range. So if it shows the which address range is how frequently accessed, and then so this is shown as colors. And so DAMON is just a profiling framework in the Linux kernel, and then profiling doesn't do anything for the memory management. And then so based on the profiling result by the DAMON, we can apply some of the memory management actions. And DAMON is for this purpose, and then it is DAMON-based operation schemes. As you can see, the blue dotted line, after passing some specific time, and based on the hotness, and then we can apply some specific actions. And then if some of the area is detected as hot, and then we can promote it to the DRAM. And if some of the area is detected as cold, and then so we can demote it to CXL. As the time goes by, and then so the pattern can be changed, and then we can apply some different actions. So in demos, and so there are many other memory management actions, but for example, the proactive reclaim, those kind of things, and then which is called the demos pageout. But there was no migration actions before. And in HMSDK, and we implemented some of the migration actions and then added it to the Linux kernel. And then that is called demos migrate hot and cold, and then which means promotion and demotion. And that is fully upstreamed, and then it is available from the Linux version 6.11, which was released last month. So to explain about the evaluation result, and then so this kind of tiering algorithm is meaningful when the workload can be fully fit into the DRAM, and so I need to increase some kind of memory pressure. So initially in the y-axis, and these are the normalized execution time, and then 1.0 is a DRAM only, the execution time. And then in the x-axis, these are the DRAM free space before loading the Redis, and then because our evaluation is done by the Redis and YCSB. So if the Redis is fully located inside the DRAM, and then so this is the fastest case, and then in that case, no tiering algorithm is needed, and then so. On the other end, if the target workload is fully allocated in the CXL, and then it has a performance overhead through the CXL protocol, latency overhead. And in terms of the slowdown, it has 18.8% compared to the DRAM only in this evaluation. And so there is a DRAM performance upper bound and then performance lower bound, and then so this is the performance range unless the target workload is not bandwidth hungry, and then so we will see the performance result in this area. So let's increase some memory pressure. So by allocating some of the cold data and in various ways, and then we can allocate the Redis in various different locations. And initially, if the partial data is located inside the CXL, and then the performance is not that bad, and then so it's very close to the DRAM only. And in the second case, half of the Redis is allocated into the CXL. The performance gets a little bit slower. And if most of the Redis is allocated inside the CXL, and then this is very close to the CXL only performance. And if we see the other cases, and then you can see the performance slow down linearly. So let's compare the result with the DAMON-enabled system. So the initial status is the same, but in this case, and we can detect some of the cold areas and then demote it to the CXL. And we can also detect the hot pages and then promote them. And then as a result, and then more Redis data is allocated inside the DRAM, and then so there's a less memory access to the CXL. And then the performance result shows that the performance overhead is minimized even if the memory pressure is severe in this case. So this result is fine, but this result was measured by turning the daemon just before the workload is accessed, but this can be for evaluation. But in the real world, the daemon can be running always on the system. So that means other cold data can be demoted earlier, even before running the target workload. And that means, okay, I can show you the result. So in that case, the target workload is not loaded yet. And then before that, we can detect some of the cold pages and then demote it. We can also detect some cold data and demote it. As a result, and then when we allocate the target workload, and then it increases more chance the Redis is allocated more in the DRAM. So as a performance result, shows much better in this case. It is very close to the DRAM only performance. So in terms of the speed up, it shows the 12.9% of speed up in the worst case. Yeah. And we upstreamed all the features into the Linux kernel, and then so we done the collaboration with the DAMON community, and this work was done. And I also presented this work at one of the major Linux conferences called Open Source Summit Europe last month, and the title is this. And I have a presentation with the demo maintainer, Sungjae Park. Yeah, and all the slide and video are already available, so you can go to the link and search it. Yeah, on the last topic, there is a heterogeneous memory allocator, and which is called a custom allocator as well. So if the user has some knowledge about their programs, they can modify their program so they know which area is cold, and so rather than depending on the OS level, the memory access profiling, and then they can just allocate some specific area as marked as cold using the hmalloc APIs. And then so HMSDK provides one library, and which is called the libhmalloc.so. And it provides some of the hmalloc APIs, such as hmalloc, hcalloc, hfree. And the interface is very much the same to the malloc and calloc free. But we can explicitly allocate some specific area to a specific NUMA node using this one. And we also provide one of the tool which is similar to the NUMA control, but which is called the hmctl. And the NUMA control applies the MEM policy globally in the process level, but on the other end, and then hmctl applies MEM policy only to the hmalloc area. it currently supports --preferred and --membind options. So there is an example. We can include hmalloc.h, and then we can just call the hmalloc and hfree. In that case, even if you're having this one and it doesn't bother anything, and the original execution shows that the entire memory is allocated into the node 0 because it didn't change the behavior. And having the HM control, and then so we can provide -m and 2, that means allocate the hmalloc area to the NUMA node 2. And as you can see, the 512 megabyte is allocated into the node 2, and you can change it to node 3. It shows it. And so we can also use it with the NUMA control as well by allocating the rest of the memory to the node 1. Yeah, so conclusion. So to conclude this one, and we have made another release called HMSDK 3.0, and then this was released last month and in September 2024, and based on the Linux 6.11. That means this is meaningful, especially this is fully aligned with the various open source projects, and the official Linux kernel can directly used for the HMSDK without any other the local patches and custom rebuild. So to sum up, and then so weighted interleaving is available from the 6.9, and DAMON-based tiered memory management is supported from the 6.11, and hmalloc allocator is available from the HMSDK 3.0. So I've already covered about the Linux kernel part, and then NUMA control, and it has a new option -w and --interleave option. There is no official release after having this feature, and so this is only available in the master and NUMA control repository. And then the third one is a demo, and then I haven't explained about this one, but the DAMON is the Linux kernel's feature. So this is fully configured with the CCFS interface, but there is a lot of knobs, and then it's quite difficult to handle all the knobs manually. So the demo maintainer also created another tool for the user space management. So in this project, and so we've also added the hardcore migration features as well. So, and we've contributed many more features as well. And other projects, and hwloc, and which is called hardware locality, and it contains lots of useful tools such as LSTopo, and it now supports the weighted interleave mode as well. And then, so I've submitted a patch and then upstreamed, and then so there was an official release as well. And lastly, and the UMF project, and Unified Memory Framework, and then that'll be presented in the next session. And so I've also proposed the weighted interleave feature in this project as well. So the final conclusion, and we are trying to expand the CXL software ecosystem on Linux, and to make CXL memory usable by end users, and such as software developers and system administrators. And so, and new memory system requires some software changes, as I explained, and especially if the major open source projects support these kind of new features, and so CXL memory can be adopted much better, because we need to lower the hurdle of using this kind of software techniques. Still, there are some kind of hurdles, so we need to lower the barrier. Yeah, that's it. Thank you very much. And then, so this is an open source project, so this is available in the GitHub, so you can find it. There is a document as well. So, yeah, thank you very much.
Great job. Thank you, man. You got us back on schedule. I appreciate it.
Yeah, I can get the question outside. Yeah. Thank you.